Hello everyone, my name is Filip Marić and I'm a PhD candidate at the Space and Terrestrial Autonomous Robotic Systems Lab at the University of Toronto, jointly with the Laboratory for Autonomous Mobile Robotics at the University of Zagreb. The title of my talk today is Of Ellipsoids and Distances, Reconsidering Robot Kinematics. Robot kinematics is defined as the study of the relationship between the dimensions and connectivity of kinematic chains and the position, velocity, and acceleration of each of the links in the robotic system. This definition suggests that robot kinematics is by no means a new area of research, and this is true. However, the goal of my talk today is to show that recent advances in computational geometry can provide new ways of formulating some common problems in this area. To this end, I will talk about two research projects that my co-authors and I are currently working on. Before we dive in, let's look at one core problem in this area. Let's consider an open serial kinematic chain, such as this simple manipulator. Given some configuration vector theta, representing the state of the joints, usually their angle, our goal is to find the corresponding operational space vector xi, which is generally the pose of the end effector or some other link. This problem is known as forward kinematics, and the mapping F is known as the forward kinematic mapping. The forward kinematic mapping F is generally a nonlinear function that can be modeled using trigonometric identities, products of homogeneous transformation matrices, or Lie group exponentials. For open kinematic chains, such as most robotic manipulators, forward kinematics is a fairly well-behaved problem that has a single solution that can be easily derived analytically. Generally, problems like reaching, grasping, and servoing require us to find configurations that correspond to a given operational space vector. This is known as the inverse kinematics problem. Ideally, we would simply use analytical techniques to invert the forward kinematic mapping. But this is difficult, and general solution strategies only exist for spatial kinematic chains with up to 6 degrees of freedom. Further, depending on the set goal and the robot in question, we know that there can be finitely or infinitely many solutions, as well as no solutions at all. This is why inverse kinematics is generally considered the harder problem for commonly used robots. A large variety of applications, such as autonomous manipulation, collaborative robotics, and teleoperation, involve robots with non-trivial kinematic structures. Regardless of the algorithm used to perform these tasks, considering the robot's kinematic mapping is crucial. Most algorithms for performing these tasks resort to numerical approaches. These approaches are commonly based on incrementally moving the end effector or some other link and iterating in order to follow a reference or until a desired goal is reached. These iterations are commonly performed by using the gradient of the forward kinematic mapping, which reveals a relationship between the operational space and joint velocities. The gradient is also known as the robot's Jacobian matrix. It allows us to control the robot's movement by solving the linear system for the joint velocities required to achieve a desired velocity in operational space. Typically, the Jacobian gives a good linear approximation even when solving for incremental operational space motions, making it a key ingredient when iteratively solving problems that involve articulated robots. So we can use this Jacobian identity to control the movement of the end effector in the operational space, either by directly setting the desired velocities or tracking a reference pose in a closed loop. However, if we were to naively implement this, eventually we would likely come across situations shown on the right. In both videos, we can see that the robot exhibits rapid and unstable movement when attempting to follow a reference path. Assuming that the assigned operational space velocities are reasonable, we can conclude that the problem is likely in the Jacobian and the identity is numerically unstable. We can analyze the Jacobian by performing a singular value decomposition and monitoring its singular values as the robot follows the assigned path. And we will notice that one or more of the singular values drops to 0 or near 0. The configurations that cause such bad Jacobian matrix conditioning are known as singularities. Clearly, we don't like singularities because they generate rapid and unsafe movement of the robot's links. At a singular configuration, the robot completely loses a degree of freedom, while even proximity to singularities results in the robot requiring large joint movements in order to perform relatively small motions with the end effector. Overall, this results in a loss of dexterity, which is highly undesirable in most applications. Luckily, it turns out that we can use geometric reasoning to develop intuitive singularity avoidance indices that can be optimized as part of control and motion planning algorithms. By self-multiplying both sides of the Jacobian identity, we arrive at a geometrical interpretation of Jacobian conditioning. First, we can equate the right side of the identity to a unit sphere in the space of joint velocities. Interpreting the left side of the equation, we can see that this sphere maps into an ellipsoid in the operational space. This ellipsoid is known as the manipulability ellipsoid, and its shape and size are strictly a function of the robot's Jacobian at a given configuration. The capacity of joint movements to produce motion in an operational space direction is proportional to the lengths of the manipulability ellipsoid axes. In fact, these lengths are exactly equal to the squared singular values of the robot's Jacobian, giving a clear geometrical interpretation of its conditioning. This interpretation has previously been used to develop indices which are optimized as part of a planning or control algorithm. The manipulability index is proportional to the volume of the manipulability ellipsoid and is often used with gradient-based optimization methods. Another common index is the so-called dexterity index, which can be related to the ellipsoid's elongation. Clearly, the proximity to singularities is best inferred and controlled by accounting for the manipulability ellipsoid's full shape, which is difficult to translate into optimization criteria. For example, the dexterity index is invariant to the overall ellipsoid volume. So, as long as two ellipsoids have the same ratios of the lengths of their shortest and longest axis, the dexterity index will not be able to differentiate between the two. Also, maximizing the manipulability index does not necessarily bring the robot further from singularities either, as high-volume ellipsoids can still have low singular values. So maximizing the volume does not necessarily mean that we're getting farther from the singularity. This leads us to an interesting idea. If there was a notion of a differentiable distance between ellipsoids, could we derive an optimization criteria that minimizes the distance between the current manipulability ellipsoid and some sufficiently non-singular ellipsoid? For example, we could set a reference ellipsoid of a spherical shape that is always larger than the current manipulability ellipsoid, forcing it to expand in order to reduce the distance. So, what is the distance between two ellipsoids? Well, we know that ellipsoids correspond to a set of symmetric positive definite matrices, which form a convex cone in the vector space of symmetric matrices. Therefore, we know that we can't just take a Euclidean distance between two ellipsoids. However, we know that this set is a Riemannian manifold, where a geometrically appropriate distance can in fact be defined. On the right, we can see that the dashed straight line in Euclidean space does not represent the shortest path between 2 points on the manifold. The shortest path is in fact the red line, whose length is equal to the length of the tangent space vector L. This geometric description allows us to reason about the differences between two ellipsoids. In fact, it has recently been shown that this characterization can be used to successfully perform manipulability ellipsoid tracking and transfer. Building on this work, we derive a differentiable geometry-aware singularity index, defined as the squared Riemannian distance between the current manipulability ellipsoid and a larger spherical ellipsoid enveloping it. We evaluated our approach by following a circular path with different manipulators, while minimizing the geometry-aware singularity index. The plots in the top row show the lowest singular values of the Jacobian matrix, which is the most direct indicator of proximity to a singularity. We can see that our method, shown in blue, results in overall higher values than those obtained by any other criteria. Notably, it obtains better results than those obtained by optimizing the manipulability index, shown in red, and optimizing the Euclidean distance between two ellipsoids, shown in gray. By looking at the maximum singular values in the bottom row, we can also see that the spherical shape of the reference ellipsoid brings the singular values closer together. Our paper, titled A Riemannian Metric for Geometry-Aware Singularity Avoidance, is currently in review for the Robotics and Automation Systems Journal, but the preprint is freely available on arXiv. Okay, so let's zoom back out to the generalized inverse kinematics problem, which is defined by setting a pose goal and/or other constraints, and then formulating a nonlinear optimization problem. Solving this problem then yields a configuration vector that we can input into the forward kinematic mapping in order to check the solution. Looking at this problem, we can see why it can become difficult. Our decision variable is the robot's configuration, theta, which is in the configuration space, while many common constraints, such as the end effector pose and collision avoidance, are defined in the operational space. As mentioned before, the mapping between these spaces is usually nonlinear. We can then ask whether this mapping can somehow be avoided by defining both the decision variables and constraints in a single space. One interesting approach to achieving this was found by Porta. He showed that the inverse kinematics problem can be defined solely in terms of distances between points rigidly attached to the robot. Further, he showed that the problem can be solved for a specific class of manipulators using algebraic methods. Inspired by this approach, my co-author Matthew Gamu and myself set out to answer two research questions. The first question is, can we adapt this approach for optimization-based formulations? And the second question is, can we extend this approach to include other common constraints as well? The key to answering the first question is obtained by arranging distances into the so-called Euclidean distance matrix. To illustrate this procedure, we can define a simple unconstrained inverse kinematics problem for the open planar kinematic chain on the right. On the left, we can see that only the diagonal elements of the Euclidean distance matrix corresponding to the points' distances from themselves are 0. Since we know the link lengths, we can fill out the off-diagonal terms with the squared distances describing the robot's structure. Next, we can set a position goal for the end effector by fixing its distance to the base joint and filling out the corresponding elements in the Euclidean distance matrix. Now, any set of points whose distances result in the Euclidean distance matrix that has elements matching those defined by the problem will in fact correspond to an inverse kinematics solution. Note that a complete Euclidean distance matrix allows us to reconstruct the point set up to a rigid transformation, allowing us to recover the full configuration vector. So the Euclidean distance matrix can be constructed directly in matrix form using the so-called Gram matrix. By arranging points into matrices, we obtain the Gram matrix using a simple matrix product. Then, the Euclidean distance matrix can be obtained by using a simple linear identity. This suggests that Euclidean distance matrix completion can be formulated as a local optimization problem over the manifold of Gram matrices of rank equal to that of the embedding dimension of the point set. Note that the linear operator omega is used to select the distances defining the inverse kinematics problem from the matrix of known distances d tilde and the distance matrix constructed using our decision variable. Naturally, this formulation can be extended to include distance ranges by adding constraints or elements to the cost function. This gives us a novel way of solving inverse kinematics numerically without using joint angles as decision variables. The problem is first defined using distances representing the goal and robot structure, along with distance ranges representing other constraints. Next, an optimization method is used to find the point set that corresponds to a feasible solution, and finally, the configuration vector is reconstructed from that point set. Earlier, we also asked whether this approach can be extended to include other constraints. In our work, we showed that this approach seamlessly allows for a variety of constraints, such as link poses, positions, and symmetric joint limits. Perhaps most notably, obstacles can be included as concatenations of spheres defined as points whose distances from the robot are lower bounded. Given that both obstacles and decision variables lie in the same space, we expect approaches based on the distance model to recover solutions more easily than conventional approaches. To test this hypothesis, we set up a simple experiment where some common manipulators are located in highly restrictive environments, and our goal is to find solutions to inverse kinematics problems when they are feasible. Here you can see the results obtained by solving 1000 inverse kinematics problems over these environments for 3 different manipulators. The yellow bars represent the results obtained by our method, while the blue bars represent results obtained by a conventional solution method based on joint angles. Our method achieves a noticeably higher success rate, solving almost 100% of the feasible problems in all environments, while maintaining a relatively low solution time that does not scale significantly with the number of obstacles. Finally, it's important to note that this formulation makes the inverse kinematics problem equivalent to other so-called distance geometry problems, such as molecular conformation or sensor network localization. These areas have highly developed solution methods that may prove effective for solving robot kinematics or similar problems in the future. This research is a joint effort by my co-author Matthew Giamu and myself. While the paper fully describing this work is currently in revision for the Transactions in Robotics journal, an extended abstract from last year's IROS workshop is available. Further, our paper showing how sum of squares programming can be used to solve inverse kinematics problems for a similar formulation was presented at last year's ICRA and is freely available on arXiv. Finally, I would like to thank you all for listening, and I would also like to thank the organizers for giving me the chance to talk about our work at this workshop. The next speaker is Professor Daniel Kodicek. He is an Alfred Filter Moore Professor of Electrical and Systems Engineering at the University of Pennsylvania. His group, CodLab, is doing very exciting research on legged locomotion, mobile manipulation, and reactive planning. Today, he'll be talking about the role of topology in robotics.